So just give me 2 shakes of a lamb's tail here to get set up. All right, Chemistry 111. So let's get into some practice on Chapter 4. This is question 4.21. And we're going to start with A. And all it says is write the ionic, and net ionic equations for this reaction. So we'll start with A, and it's silver nitrate plus sodium sulfate. There we go. So we need to figure out the rest of this equation. All right, so let's do it. I'm going to move this over just a tad. Now, I'm going to give you the instructions for exam 2 very soon. I don't ask you to memorize the entire solubility table. There's a little part of it that I ask you to memorize, and I think that's just the first 2 rules, which are the easiest ones of all. So basically, the only rules I ask you to memorize are the ones about alkali metals, compounds, and the ammonium ion, and then nitrates and acetates, I think. I'll have to go back and double check, but I only ask you to memorize a couple of them. So basically, all the exceptions, I give them to you. Okay, so you're not going to be, oh, I forgot or something like that. So let me help you out with this if you don't have a solubility table nearby, but we're going to combine silver, right? We're going to combine silver and the sulfate ion, and then we're going to combine sodium and the nitrate ion. So we would end up with silver sulfate, so that's Ag2SO4, plus we end up with NaNO3, okay? Sodium nitrate is definitely a soluble compound, but silver sulfate, if you go to the solubility table and you look at sulfates, you'll see that sulfates are soluble. An insoluble exception, though, is a silver, okay? When we have a silver as our cation. And so silver sulfate is actually a solid like that. Now we need to balance it out. We got 1 silver here, we got 2 over here, and so we're going to need to put a 2 there. Let's see, we've got 2 sodiums here, but we've only got 1 here, and so we need to put a 2 there. And when we do that, we end up with a perfectly balanced equation. Okay, so that is actually our molecular equation. Okay, we've already got that part done. Now we're going to write out our ionic equation. Sometimes we call this the total ionic equation, right? That's what I called it in class and lecture. So let me just move that over, and we'll call this, call it the total ionic equation. Now, can anybody tell me what are we going to break up into its ions here in our total ionic equation? And it is not a trick question. Can anybody tell me what we would break up into ions here? Not everything. There we go. Okay, Christian, you're close. It's almost everything, but it's exactly, Davey, it's anything aqueous. Okay, so when we have a solid, we're never going to break that apart into its ions because it's not going to ionize, right? It's a solid. It's not going to dissolve. So let's write everything out into its ions. So we have 2 silver plus ions that are aqueous plus 2 nitrate ions that are aqueous. We've got 2 sodium cations that are aqueous. We've got a sulfate ion that is aqueous. Remember, we don't break up the silver sulfate, so silver sulfate is still a solid, that didn't change, plus 2 sodium ions that are aqueous, plus 2 nitrate ions that are aqueous. Whew, just made it, okay? Anything that's the same on both sides of the arrow, we're going to cancel that out because those are spectator ions. That's the nitrate ion and the sodium ion. So again, here we cancel spectator ions, okay? And then we end up with the net ionic equation. And let's write the net ionic equation. It's everything that's left over. We end up with 2 silver plus ions plus the sulfate ion, and we produce silver sulfate, solid like that. All right, that's all there is to it. Let's try one more. Let's try 14.21. Let's try C. Okay, let's try C. So let me write it down here. So this is 4.21 C. And again, if you have your textbook, it might be faster for you to follow along on that rather than waiting for me to scribble everything down. Okay, so we've got ammonium carbonate plus calcium chloride. We're going to combine the ammonium and the chloride, and we're going to combine the calcium and the carbonate. So calcium carbonate is CaCO3. Plus, we're going to end up with ammonium chloride, so NH4Cl. Again, if you go over to the solubility table and you look up ammonium chloride, it is soluble. However, if you look up calcium carbonate, when you get to carbonates, you see that carbonates are insoluble except for compounds containing alkali metals in the ammonium ion. Well, calcium is not an alkali metal, it's an alkaline earth. And so calcium carbonate is a solid and ammonium chloride is aqueous. So that's our molecular equation. Now we need our total ionic equation. Everything that's aqueous, we're going to break apart into ions. So we have 2 ammonium ions plus a carbonate ion. 6 minus 3 here. There we go. Plus, we got calcium 2 plus ion plus 2 chloride ions. Produce calcium carbonate. It's a solid. Plus, oh, did I not balance this thing out? There we go. Am I balanced now? Cha. All right, it's perfectly balanced. Anyhow, is that what somebody wrote here? Yeah. Thanks, Kristen. I didn't even notice that you'd written that. Anyhow, so we have 2 ammonium ions, aqueous, plus 2 chlorides, aqueous. All right. So we're going to cancel the spectator ions. That's going to be the ammonium ions, and that's going to be the chloride ions. And we're left over with our net ionic equation, which is going to be calcium 2 plus aqueous plus the carbonate ion aqueous produces calcium carbonate, which is a solid. There we go. Hot diggity darn. Let's move on. Let's see here. I had some other ones. Let me go back to the textbook here. Let's try some balancing some acid-base reactions. And I don't know if we're going to do all of these. But let's try 4.33. And I want to do this more to practice balancing the equations. So this is a 4.33. Why don't we start with A? So we're starting with HBr, which is hydrobromic acid, okay, plus ammonia, which is a base. All right, so this is an acid, and this is a base. So it asks you to balance the equation, then write the ionic and the net ionic equations. Anyhow, we'll see here. But we know from Bronsted-Lowry that the acid is going to donate a proton, and the base is going to accept a proton. So if the acid donates a proton, I'm going to end up with Br minus left over, so just the bromide ion. And if the base accepts a proton, I don't have NH3, I have NH4 plus aqueous, like that. Okay, so there we go. There's our molecular equation. My question to you is this balanced the way it is? Hydrobromic acid plus ammonia. Is this balanced the way I've got it? Yeah, absolutely it is. Yep. Okay. So let's write out the ionic equation. We'll do it quickly. So the total ionic equation is going to be a proton plus bromide plus NH3, right? That's not going to break apart into ions because it's not a strong base. And then we have bromide aqueous plus NH4 plus aqueous. Okay. Well, what's a spectator ion that can cancel? The only thing that can cancel on both sides is the bromide ion. And so my net ionic equation is just going to be H plus aqueous plus ammonia produces the ammonium ion. Nothing more than that. All right. Let's see. Let's try something different here. Number 4 point. Okay, let's try 4.44. And maybe we'll take a break here. So this is question 4.44. Let's do the first one together. It says, for the complete redox reactions given here, write the half reactions and identify the oxidizing and reducing agent. So let's see here. We've got 4Fe plus 3O2 gives you 2Fe2O3. Okay, so this is some kind of redox equation. So that means that something is being oxidized and something is being reduced. Now, if you look over here, I have pure iron and I have pure oxygen, right? Iron is Fe, oxygen is O2. So that means that the oxidation state of iron is 0, right? Pure iron doesn't have any charge. The same thing with the oxygen. It doesn't have any charge. However, if I look at this here, Fe2O3, I can use the rules that we looked at in our last class where we determined oxidation number, and I can use those to determine the oxidation state or oxidation number of the oxygen and the oxidation number of the iron. Now remember that iron is a transition metal. It actually has two oxidation numbers. It can either be +3 or +2. However, oxygen is almost always -2. Now if I've got -2 times 3, that gives me overall -6. So that tells me that my iron has to be overall +6, but I've got 2 irons, don't I? So +6 divided by 2 means that the oxidation number of my iron is +3. So let's erase this. We'll tidy it up. And again, we know that our oxygen is -2 and our iron is +3. Now we can examine our redox equation and we can determine what's oxidized and what's reduced. Let's take a look here. I'll use the green pen. So we're going from iron 0 to iron 3+, and we're going from oxygen 0 to oxygen 2-. Remember the acronym oil rig. Oxidation is losing electrons and reduction is gaining electrons. And so if the iron is going from 0 to +3, it must be losing electrons, right? Electrons are negative. When you lose something negative, you become more positive. And so the iron is being oxidized. So this is the oxidation half reaction. You can see that the oxygen is going from 0 to -2, so that means it's gaining electrons. Reduction is gaining electrons. So this must be the reduction half reaction. It also asks us to identify the reducing agent and the oxidizing agent. If the iron is undergoing oxidation, that means it's causing the reduction of the oxygen. Therefore, the iron is the reducing agent, and the oxygen would be the oxidizing agent. Okay, for the same reason. The oxygen is causing the iron to become oxidized to iron 3+. All right. So with that information in mind, I would like you to try a few more. Okay, so I want you to try B. So we'll take a look at B and I'll write it down here. So B is chlorine plus 2 sodium bromide gives you 2NaCl plus Br2. And then I want you to take a look at the next one, which is silicon plus 2 moles of fluorine. That gives you SiF4, like that. And so why don't we take our break here? It's 5:58, so why don't we come back in 10 minutes, and you can give these questions a try. I don't think it'll take you 10 minutes. And it's 6:08. We'll come back, and we'll get back to it. All right, well, let's get back to it here. Let's try 4.44b. So I'll go a little quicker this time. If we take a look at the oxidation state of the chlorine, it's 0. If we take a look at the sodium and the bromine, the sodium is 0, and the bromine is -1. Sorry, did I say the sodium was 0? Because I meant +1. There we go, because it's an ionic compound. Anyhow, then if we go over to the other side, we have sodium chloride, so the sodium is still +1. The chlorine is -1, and the bromine is 0. So the sodium remains unchanged. However, the chlorine is being reduced, isn't it? So this is reduction. This is going from 0 to -1, and the bromide is losing electrons, and so it's being oxidized. Oxidation, okay, like that. And so that would mean that the chlorine is the oxidizing agent, and that would mean that the bromine is the reducing agent. Let's look at the next one here. So I have silicon and fluorine. Both of them have an oxidation number of 0 for the silicon and 0 for the fluorine. In silicon tetrafluoride, fluorine is always -1. That's a rule that we looked at. If we have -1 times 4, that gives us -4, which means our silicon must be +4. So our silicon goes from 0 to +4, and it lost electrons. Losing electrons is oxidation, so this is oxidation. That would mean the silicon is the reducing agent. Okay, in the fluorine, it's going from 0 to -1. It is gaining electrons. Therefore, this is reduction, and the fluorine is the oxidizing agent. All right, give me a thumbs up if you follow me on a little bit more on oxidation and reduction. Okay, well, what I thought we would do now is we would try question 4.46. So question 4.46, it says, phosphorus forms many oxoacids. Indicate the oxidation number of phosphorus in each of the following acids. So we have A, which is HPO3. We have B, which is, we won't do all of these, H3PO3. We have C, which is, so B was H3PO2, and C is H3PO. Anyhow, with this, we should be able to get started in practicing the concept of oxidation number. Okay, so let's start with H3PO3. I'll write it over here. So we have HPO3. HPO3. Well, we know that the hydrogen must be +1 because it's a proton. So that means that the PO3, the whole thing is -1. So we can rewrite that over here, PO3, and it's got a -1 charge. Now, one of the rules that we learned is that oxygen is almost always having an oxidation state of -2. And we have 3 of those, which gives us -6. Now, if the oxygen equals -6, something plus -6 is going to equal -1, right? Because the overall charge of the PO3 ion is -1. So the answer would be that X would be equal to +5. So that means that my phosphorus is +5, so +5 here. My oxygen is -2, and my hydrogen is +1, like that. Go over to the next one. So now we've got H3PO2. Give it a shot. We've got H3PO2. Each one of the hydrogens is +1. So we have +1 for each hydrogen. So if I have +1 times 3, that tells me that overall here I have +3, which tells me that my PO2 ion must be -3, right? Okay, or I should say, yeah. There we go, is -3. So if we go back to our rules, we know that oxygen is minus 2. Yeah, is minus 2, and I've got 2 of those. So that equals -4 overall. Now for my phosphorus, I have something plus -4 is going to equal -3. So the answer would be x is equal to +1. So that tells me that my phosphorus is +1. So +1 minus 2 and +1 over here. Let's erase that. And let's try the next one, which is H3PO3. So I have H3PO3. Let me rewrite it here. H3PO3. This is phosphorus acid. Anyhow, we have our hydrogen, which has a charge of +1. I have 3 of those. That means that overall this is +3, which tells me that the PO3 ion must be -3. Okay, so if it's -3 and my oxygen is -2 times 3, because I've got 3 oxygens, which would give me -6, but the overall charge of my ion is -3, so that means that x plus -6 gives me -3. And so the answer is x must be equal to +3. So my phosphorus here is +3, my oxygen is -2, and my hydrogen's oxidation number is +1. Does that help anybody who is maybe struggling a little bit with oxidation state? Does that help anyone? Hope so. All right, let's try another one. Let's see here. Why don't we try 4.47? We'll pick a couple of them here. Now, in the book, it asks you just to identify the oxidation number of one particular atom. Let's try a couple of them here. Let's try, so this is 4.47. I'll just pick out a couple. We'll do CLF. Let's do C2H2. Let's do K2. Oops. K2O4. So let's try these ones here. I'll give you a second to look at them before we start going at it. Give you a minute or two. All right, let's take a look at the first one. CLF. One of the first rules that we learned was that fluorine is always -1. No exceptions. You can bet your bobby socks on that. There will never be an exception to that. So if I have -1 here, that tells you that the chlorine must be +1. If we look at the next one, C2H2, another rule that we learned is hydrogen is almost always +1. Again, the only exception to that are when hydrogen is combined with an alkaline metal or an alkali earth. Okay, so if you had something like CaH2 where hydrogen is second, here it would be -1. So the calcium is +2. But again, that's when you have it combined with a metal. Carbon is not a metal, it's a non-metal. And so our hydrogen is +1. We have +1 times 2 gives you +2. So that means that over here, you must have a total of minus 2, and you've got 2 carbons, so that means negative 2 divided by 2, so that means your carbon is minus 1. And for the next one, you have potassium chromate. Now, the easiest way to do this is probably to memorize the chromate ion, right? So potassium is in group 1A, so it's plus 1. The chromate ion, I'll rewrite it over here, is CrO4 2 minus. Okay, we have our oxygen, which is negative 2 times 4, which equals negative 8. Now something plus negative 8 equals negative 2. So the answer is plus 6. So that means that your chromium is plus 6 and your oxygen is minus 2. Okay, well, that's some pretty good practice on oxidation numbers. Let's see here. Oops. There we go. And let's move on to something a little different. Let's try question 4.64. So if you go to the book and you look up question 4.64, question 4.64, it says describe how you would prepare 250 milliliters of a 0.707 molar sodium nitrate solution. So you want 250 milliliters of a 0.707 molar sodium nitrate solution. Okay, so how would you do that if you're in a lab? Well, sodium nitrate is an ionic compound, right? Sodium nitrate is ionic. It's made from a metal, sodium, and the nitrate, which is a polyatomic ion, but it's made completely of nonmetals. So sodium nitrate is a solid at room temperature, right, when it's not in a solution. So if you had some sodium nitrate, all you'd have to do is weigh out the correct mass of sodium nitrate, put it in a 250 ml volumetric flask. So you put your sodium nitrate in there, right? And then you would dilute it with water, okay? And you'd make a solution of the sodium nitrate in water up to 250 mils, and you'd have your solution, your 0.707 molar solution. But the question is, how many moles of sodium nitrate do we require to make this? Well, we want to have 250 milliliters. Now I'm going to convert that to liters. It's 0.250 liters. I just divide by 1,000. So let me just move this, my volumetric flask, out of the way here. Okay, so if we have, if we have 0.250 liters of solution, which is what we want, and we want the concentration to be 0.707 moles per liter. If I was to multiply these two, my volume would cancel, and I'd end up with the number of moles of sodium nitrate that I would require. But I can look up the molar mass of sodium nitrate from my periodic table. It is 85.00 grams per mole. So I can use that conversion factor. I know that in 1 mole of sodium nitrate, I have 85.00 grams of sodium nitrate. Look at this. Moles cancel out, and I'm left over with the number of grams of sodium nitrate. And so when I punch all that spinach into my calculator, I end up with what? I got 15.0 grams of sodium nitrate. And so what we would have to do is we would mass, is the same thing as weigh, but mass is more correct because you can measure it on a balance. Mass 15.0 grams of sodium nitrate. Okay, then dilute to a volume of 250 milliliters, and that's what you would do to make that solution. Let's try a little bit of question 4.68, not the whole thing. First part, it says 4.68, there's a few parts to it. We'll just do Why don't we try C? Let's do C. So it says calculate the molarity of the following solution. So it says 7.82 grams of what's called naphthalene, which is essentially mothballs. And it tells you the formula C10H8 in 85.2 milliliters of benzene. Okay, so you make a solution instead of dissolving it in water, you're putting it in benzene, which is just a different liquid. Okay, so if we want to know the concentration or the molarity is equal to the number of moles per unit volume. We have the number of milliliters, and we can convert that into the number of liters. So we divide that by 1, 2, 3. So that's going to be 0.0852 liters. But over here, we need the number of moles of C10H8. Well, first, let's calculate the molar mass of C10H8. We have 10 carbons, so in C10H8, we've got 10 times 12.01 grams per mole, plus 8 times 1.01 grams per mole, right? This is for my carbon, this is for my hydrogen. And when you do that, you end up with something, and I'll just cut to the chase here. I've done it already, which is 8.08 plus 10 times in my head, couldn't I? It equals 128.18 is what I got here. So 128.18 grams per mole. Okay, so in order to figure out the number of moles of my naphthalene, I'm going to take my mass, 7.82 grams of naphthalene, and I'm going to divide it by 128.12 grams of naphthalene in 1 mole of naphthalene. I'm going to divide all of that by the volume, 0.0852 liters. You can see that grams of naphthalene cancel. I end up with the number of moles per liter. So 7.82 divided by 128.1. There we go. No, hold on. Did I write 128.12? Let me double check that. 120.1 plus 8.0. Yeah, it should be 128.18. There we go. Anyhow, it's fixed now. So when you put all that in your calculator, you should end up with 0.716 molar naphthalene. And so that is our final answer, calculating a concentration. Let's try 4.70. So 4.70, it says determine how many grams. So this is 4.70a. Says determine how many grams of each of the following solutes would be needed to make 250 milliliters of a 0.1 molar solution. So we want 250. They write it in scientific notation as 2.50 times 10 to the power of 2 milliliters, which is the same thing as 250 with 3 sig figs milliliters of a 0.100 molar solution. Okay, and we're going to make it an A from cesium iodide. Okay, well, all we need to know is how many grams of cesium iodide we would need, because cesium iodide is going to be a solid. It's made from a metal and a non-metal. It's an ionic compound. Well, in order to do that, we need to know the number of moles of cesium iodide that we need, and we need to know the molar mass of cesium iodide. Now, I've already gone ahead and looked that up. The molar mass of cesium iodide, I just Googled it, is 259.81. Again, you won't be able to use Google on your exam, but I'm sure that you all know how to calculate a molar mass by now. So we have our molar mass. We have the volume and we have the molarity. Now I know that molarity is equal to the number of moles times the volume. That means that the number of moles, in this case of my cesium iodide, is going to be equal to the molarity times the volume. So all I have to do is take 0.100 molar, which is moles per liter, multiply it by this volume. I'm going to convert that into liters. It would be 0.250 liters. I just divided by 1,000 in my head. So multiplied by 0.250 liters. The units of liters cancel out. And so I have 0.0250 moles of cesium iodide, which is what I need. Okay. So then I take the molar mass of my cesium iodide, 251.81 grams per mole, and I multiply that by 0.0250 moles. Moles cancel, and I'm left over with 6.30. What am I doing wrong here? 251. It's 259.81. I'm making all kinds of mistakes here. There we go. So 259.81 times 0.025. There we go. Gives you 6.50 grams of cesium iodide. Give me a thumbs up if you feel like you could nail that question. You're like, Mr. Dion, I can do that one. Not too bad. All right. Nobody? Is anybody there? All right, cool. All right, thanks, you guys. Great. Well, let's try some more. Anybody enjoying this or just me? Let's see. Let's try 4.74. Yeah, let's try 4.74. So this is question 4.74. It says water is added to 250 mils. So you have 25.0 milliliters of 0.866 molar potassium nitrate. Okay. If you dilute with water to 500 milliliters, what is the concentration of the potassium nitrate? What would the concentration be in this case? Could anybody tell me what formula we would use to solve this problem? Anybody have an idea where we might start in terms of formulas? Yeah, thanks, Anthony. Absolutely. M1V1 is equal to M2V2. You can write it as M initial times the initial volume gives you the final molarity times the final volume. You can call it C1 times, C1V1 is equal to C2V2. I don't care. As long as you understand what's going on. But this is a dilution problem, right? And so dilution, so we'll put dilution problem. Therefore, we're going to use M1V1, call it the way Anthony called it, is equal to M final times volume final, right? We have our initial volume, we have our initial concentration, and we have our final volume. So that means that we can solve for our final molarity. Let's do that. So our final concentration or molarity is going to be equal to the initial volume times the initial molarity divided by the final volume. All we got to do is plug in some numbers, right? Nothing more than that. So we have 0.866 molar multiplied by our initial volume, which is 25.0 milliliters. Divide that by the final volume, which is 500 milliliters. Notice, and I went over this with you in the last lecture, I said you don't have to convert these to liters because they're going to cancel anyway. So you have 25 divided by 500, multiply that by 0.866, double check my math, and you end up with 0.0433 molar. That's going to be your new solution concentration. Notice that I have three sig figs here, here, and here. So I have three sig figs in my final answer. Also, you can always ask yourself, does this answer make sense? Right? You're going from something that's got this molarity and you're diluting it. So it should be less concentrated, and it absolutely is. Does that make sense? All right. Well, with that in mind, let me just find another one here. Let's try a titration problem. Yeah, let's do another titration. Let's try 4.90. Let's try 4.90. Okay, and I'm going to give you guys a few minutes to work on this one. I'd like you to try this one without my help. I'll just get you started here. It says calculate the concentration of sodium hydroxide solution. So the concentration is what? That's what we're trying to solve. If 25.0 mils of NaOH is required to neutralize required to neutralize 17.4 milliliters of a 0.312 molar HCl solution. So I'd like to give you a couple of minutes to try this. I'm not going to give you the balanced equation. I'd like you to try to figure that out yourself. It's not a trick. No trick here. I'll just give you a couple minutes to give it the old college try. Okay, let's give this one a try. And I won't ask if anybody's got an answer. Let's just go for it. So we're neutralizing HCl with sodium hydroxide. So we're combining sodium hydroxide plus HCl. Sodium hydroxide is a strong base. Hydrochloric acid is a strong acid. So we're going to end up producing a salt. In this case, the metal will be sodium. The non-metal will be chloride. We're going to end up with sodium chloride, which is our salt, plus water. Now you see that this equation is already balanced in this form. And you can see that the stoichiometric ratio of sodium hydroxide to hydrochloric acid is 1:1. Okay. Well, if we want the concentration of our sodium hydroxide, all we need are the number of moles divided by the volume. We've already got the volume. It's 25 milliliters. 25 milliliters is 0.0250 liters. So we need to figure out the number of moles of sodium hydroxide. Let's start by writing down what we know. We have 17.4 milliliters of our HCl solution. I'm going to convert that into liters. Again, just divide by 1, 2, 3, 1,000. So I end up with 0.0174 liters of HCl. I know that my solution is 0.312 moles of HCl in 1 liter of HCl. Look, if I was to stop here, my volume of HCl cancel, and I just have the number of moles of sodium hydroxide, but I want the number, the moles of HCl, but I want the number of moles of sodium hydroxide. But look, the stoichiometric ratio is for every 1 mole of HCl, right? I use 1 mole of sodium hydroxide. So 1 mole of sodium hydroxide. Now you might be saying, Mr. Dion, I don't even need to put that conversion factor in there because I know it's 1:1. No problem. No problem at all. You don't have to include it if you don't want to. I just want you to get the right answer. All right, so we end up with 0.00543 moles of sodium hydroxide. And now I can plug this number into my numerator right there. Let's do it. So we'll put in our 0.00543 moles, divide by 0.0250 liters. 0.0543 divided by 0.25 gives you 0.217 molar sodium hydroxide, and that is the final answer, like that. Did anybody get that one? Okay, great, good. Well, let's try one more, and I think that's all we'll have time for. We don't want to pick anything too difficult because we're going to look at the practice exam as well. Let's try 4.91 quickly because it uses the same formula. Let me go back to it here in the book. So 4.91. So 4.91, it just says 4.91. It says calculate the volume in milliliters of a 1.420 molar solution required to titrate the following. So if you have 1.420 molar sodium hydroxide, how much is it going to take? Your volume of sodium hydroxide is going to be what? That's required to titrate 25.00 milliliters of a 2.430 molar HCl solution, like that. Okay, there are so many ways that you could set this up. You could set this up all in one fell swoop. You know, the solution manual probably has some ways of doing it, et cetera, et cetera. I'm just going to show you a different way. Maybe it's a way that's a little bit different. And this is for people who may be struggling with dimensional analysis and setting everything up. Look, you can solve problems like this stepwise if you want to. I don't like to do it that way, but if you want to, it's totally acceptable. You're starting it with 25 milliliters of your HCl solution. Now, 25 milliliters divided by 1,000, we move the decimal place over 3 places. We end up with 0.02500 liters of HCl. We know the concentration of our HCl. It's 2.430 moles of HCl in 1 liter of HCl. Let's just do that one step. So if we take 2.430 multiplied by there we go. We end up with 0.0608. No, we should have 46, shouldn't it? 6075 moles of HCl. Now, from our last problem, we know that the ratio of sodium hydroxide to HCl is going to be 1:1 when we use these to titrate each other. So we know again that the number of moles of HCl is equal to the number of moles of sodium hydroxide. Therefore, the number of moles of sodium hydroxide is also going to be equal to 0.06075 moles, right? We've got that. So now we've got the number of moles and we've got the concentration, right? We said that molarity is equal to the number of moles over volume. So that means volume of the sodium hydroxide solution is going to be equal to the molarity of the sodium hydroxide solution multiplied by the number of moles of the sodium hydroxide solution. So our volume of NaOH is going to be equal to 1.420 moles per liter multiplied by, shit, I've rearranged my formula incorrectly. Mr. Dion is very tired. Okay. I'll use my 3-month-old baby as an excuse, and I'll fix this. So we have our volume is equal to the number of moles of sodium hydroxide, sorry about that, divided by our molar, our concentration of our sodium hydroxide. That looks a little better, doesn't it? So we have the number of moles, which is 0.06075 moles divided by our concentration, which is 1.420 moles per liter. So we take this, divide by 1.420, and we end up with 0.04278 liters. And then you can do another step, 0.04278 liters. You know that in 1 liter, there's 1,000 milliliters. Do that. So multiply by 1,000, and you end up with 42.78 milliliters of the sodium hydroxide stock solution. So that's the final answer right there. Now, again, I don't teach this way, and I don't expect my students to solve problems this way, but there's no problem with it, really, okay? If you have to do everything stepwise and you get the right answer, that's okay. There's really nothing wrong with it. If you understand what you're doing, there's nothing wrong with it. I prefer to set everything up in dimensional analysis. I find it easier, but I just want to make you aware that if you're the kind of person who likes to do, step 1 and then step 2, and step 3, that's totally cool. It's totally fine as long as you understand what you're doing. Okay, don't ever be intimidated and say, well, I have to do it by dimensional analysis, or I'll never pass the class, because that's not true. Oh.